Hello and welcome to this another week of our online lecture on multimedia. And this week we'll be trying to understand, data compression basics and more appropriately image compression. So this is the first week lectures on data compression, and after some basics we'll be focusing on image compression, and the next we'll be learning on audio compression, and the next week we'll be learning video compression. So see here that as far as this image compression is concerned, so here are two photos, right? In the left photo and the right photo, and this photo looks almost similar photos, right? As we look, the same photo in fact. But if you carefully follow that, perhaps this photo quality is a little better compared to the right one, and but this photo takes more storage, that is 343 kilobyte. However, this photo takes less storage, so that means this is a compressed image, and this compression is basically JPEG compression. JPG image, right? In camera and many applications we use that. So the advantage of this compressed image is if we like to store, so it takes less amount of memory. And if you like to transmit this image from your place to somewhere else, it takes less time to transmit. Also, it takes less bandwidth. So there are various kinds of advantages that we can have from compressed image. And this is the lecture that we'll be talking on this compression stuff. So if you carefully take these lectures, you will be understanding some useful things on that. So let's see what will be what we'll be trying to cover. So first we will see some basics on data compression, some terminology more appropriately, and that terminology is inappropriate for our understandings on compression techniques. So then we'll be starting the compression stuffs, and primarily we divided the whole compression techniques into two categories broadly. So one is lossless compression techniques and another is lossy compression techniques. So we will see both of them. So what is compression? So compression is basically some sort of coding that will effectively reduce the total number of bits needed to represent certain information. So if we have any information, like whatever information, it might be a message or it might be in any things, it's image or video, but computers understand all of this information in terms of 0, 1, 1, 0, something like that, right? So essentially we will compress the number of bits requirements. So this is a general data compression scheme framework that we can understand. Let's say we have some data, we sometimes say input data, and we pass this input data to compression, to compress this data. And we also technically we say this is basically an encoder, okay? And then this compressed information either we can store or we can transmit through a networks. Then when we transmit the information, definitely we need to receive by somebody. So that receiver need to decompress that image, that data, because this is a compressed, he received the compressed data, but at the receiver definitely it needs to uncompress or decompress so that the original data come back. And this decompression we also say decoder, right? So either things we can say. So ultimately what we have an input data, so this data will compressed, and this compression definitely we at the output level we need to decompress it. So that's the basic mechanism. Okay, now let's say before compression, the number of bits that we need to store the information that we are talking about, and let's say B1 is the number of bits after compression. The same data before compression, let's say we need B0 number of bits, and after compression we need B1 number of bits. So then we define something called compression ratio. So compression ratio is B0 over B1. Now as you understand, if we can achieve some compression, so definitely B1 greater than B0, because B0 greater than b1. So because if we can compress, definitely the number of bits after compression, that is less than b0, right? So this ratio is always greater than 1. And if this ratio is much higher than 1, larger than 1, we say the compression is also much more. Okay, now we define another terminology that we saw. One is lossless compression, another is lossy compression. When you do the compression stuffs, so that means we need to perform compression, and at the receiver side, or when we let's say we store the data at some computer or some hardware or some memory, definitely when we read that data again for our needs or by some applications, we need to decompress, right? Now this compression and decompression process definitely makes the compression system. Now in the compression systems, either in compression or decompression, when it happens, if we don't lose any information, then that compression decompression process or that compression technique or that compression scheme is lossless. Otherwise we say lossy compression. So we have both applications. Sometimes there is situation that we can't lose any information, for example medical data. So if we compress the medical data, or if we compress text data, for example in email, we can't lose any information. So that's called lossless information. But however, image and video, sometimes it's okay, or audio, sometimes it's okay to lose some information. Still we can see the image, we can see the video. So that's the idea why we use lossless compression and lossy compression. Definitely lossy compression is requires very less storage compared to lossless compression. So let's see then. So when we study this compression decompression stuffs, it is necessary to at least understand this basic reference, this called entropy. Okay, so something called entropy that we need to a little understanding on that. We will not understand very deep details because this is coming something from information theory, but for our things, for image or audio video, just we need that how we calculate entropy. Okay, so let's say we have an information source, and this information source has a symbol S1, S2, and up to Sn. That means by using these information symbols, our information has been built. Okay, or in other words, let's say we have a message. For example, this is a good book. Okay, so this is a good book. This is basically let's say a information and or a message, whatever. And you see, so in this information we have T, we have H, we have I, we have S. So these are basically symbol. Each space is a symbol, right? So these are symbols. So in the same way, let's have somehow we have the information. This information is S, and this is our symbol S1 up to Sn. There are n symbols. So in this case, how to define entropy? Okay, so now let's say that probability that if we randomly select, if we randomly take one symbol out of this message, then what is the probability of S1 and what is the probability of S2, something like that. Let's say probability of occurrence of S1 is P1, and the probability that it will be S2, that probability is, let's say, P2, and in this way this probability, let's say, Pn. If this is the case, then we can define the entropy in this manner. Let's say we just take this probability and we just do inverse of that. So that means 1 upon this probability, and we take log 2 of that, and then we multiply these terms with this same probability P1. Okay, now let's say we calculate in this way for all of these things. That's P2 log 2 1 over P2. Okay, so this is this one, and then plus up to in this way Pn, in this way, let's say like this in dot dot dot, and I'm just writing here Pn log 2 1 over Pn, right? So that means just we write the same pattern and n number of times. So then what we can do, we can just sum up all of this term exactly like this one. See, n I equal 1 up to n, then pi log 2 1 plus pi. Now this is, we say entropy. Okay, now if we just do this, let's say this 1 over pi, we can write this pi, let's say minus 1 in this pattern. Now if we just take minus 1 here, so that means this 1 over pi, we can write directly this one. So either way we can write. Okay, so as you know, the probability is always somewhere between 0 to 1, always somewhere between 0 to 1. So that's why the 1 over pi, and if we take log of 2 this one, so it will be always coming negative, and that's why if we have negative here, so it will be again the positive one. So that's the idea. So for example, this number will be negative, this log 2, and this negative, so it will be positive. Anyway, so this is the things, okay, that how we define the entropy. So now let's say we have this entropy. Sometimes we also write in this pattern that entropy of S, and how we define then, just summation I equal 1 up to n and pi, and then multiplied by log 2 1 over pi. So this is what is this information. Now definitely we already know this pi is the probability that symbol Si will occur. Now what is this one? Log 2 1 over pi, and what is entropy physically? This is generally for information theory, but for our case, we don't need to understand that how it comes and what is the details, but just we'll define this one because we'll use this as a scale and measurement. Okay, anyway, so this one, this log 2 1 over pi, this somehow, let's say we know, let's say somehow it represent amount of information that this particular symbol Si, for example, let's say log 2, we are thinking about, let's say Si, a particular symbol Si out of this S1 S2 up to Sn. Now we are thinking only this, let's say that symbol. Now this symbol, how much information it has, okay, how much information it indicates, or how much information it has. So these things we can represent, let's say somehow in this pattern. Okay, so this is the amount of information that is associated with this Si. That's it. Let's say we understand this one. Okay, now this one we multiplied with its probability, that is pi. So that means when we take this summation, then this becomes entropy, to us is basically become the average amount of information that contains a particular symbol on an average, right? So this is our total information is 1, and let's say a particular symbol Si, how much information it contains, that information is, let's say log 2 1 over pi, and then if we have, then you can multiply this one by this corresponding probability, and if you just take summation of all of them, then it's become the expected values or average values. So that means this entropy, this one eta or ASS, is represents that on an average a symbol in this information source, how much information it carries, so on an average. Or in another words, we can say, because it depends on this base is 2, so we can say that number of bits needed to represent this one symbol. So this is what it is. Okay, so that means if our entropy is, let's say eta, and we know that a particular symbol Si, on an average, if we like to represent this information by 1 and 0, then we know that it requires eta number of bits on an average. So if there are n number of bits in our information, then total number of bits that we need is n multiplied by eta. So that's what it is. Okay, and definitely if you see that if our probability is decreasing, let's say probability 0.2, then the entropy is, let's say amount of information, this one, this is 2.32. Okay, and let's say somehow a symbol has a probability 0.7, then the amount of information that it carries is log 2 1 over 0.7, that is 0.51. And if some information, if some symbol has a probability 1, that means a very certain symbol, that information is 0. That means if something is certain, so there is no uncertainty. Because there is no uncertainty, so we don't need to represent that one. Okay, so anyway, so this is all about whenever we design any compression techniques, we need to compare this with some sort of entropy. Now you'll be talking on that more little later. Now let's say we take an example that how we can calculate the entropy. Okay, so to calculate the entropy, so we just think let's say we have an image. Okay, let's say we have this image, and this image is black and white image. Okay, let's say that's a black and white image, or we can say binary image, right? Binary image. Now if this binary image, that means we only have some symbol 1 and somewhere is 0. Each pixels is 1 or 0 somewhere randomly. And let's say 1/3 of this symbol, 1/3 of these symbols are, let's say, black pixels. Okay, and remaining pixel, let's say 2/3 of these pixels are white pixels. Okay, so we can say that we have only two symbols. If we can consider that this image is an information, then we can say there are two symbols. One is 1 and another is, let's say, one symbol is 0 and another symbol is 1. So this 0 might be, we can say maybe this is the black symbol and this is the white symbol. Now what is the entropy for this information? So that means on an average, that how many bits we need to represent or to store this one symbol in this information or in this image. So that's the idea. Now see, we can then imagine that what is the probability of this symbol? What is the probability of this symbol? Definitely this probability is 1/3, because 1/3 symbols are black symbols. So if we just take this probability and then we take log 2 1 over this probability, plus we have another symbol. Another symbol is this one. What is this probability? This probability is 2/3. So 2/3, and then we take log 2 1/2/3. Now if we these things, then if we just then means all symbols we calculated. Now if you just calculate the entropy, so this entropy is becoming, you see, 0.92. 0.92 is the entropy. Okay, so 0.92 our entropy. So and let's say we have now another image, and that image, let's say we have gray level image. Okay, gray level image. Now in this gray level image, so definitely there's gray level is from 0 to 255. So that means there are 256 different gray levels. Okay, and definitely if we have 256 different gray levels, to identify those levels we need 8 bits for each pixels. That we already know this. So we need 8 bits in general to represent this one, right? And we don't know that which pixels what level, but let's say each pixels has equal probability. So that means if there are 256 different levels, so we can say that the probability that each pixels might take either 0 level or 1 level, or in this way we might have 255 levels, right? Level 255. Now if we randomly select, what is the probability? There are 256 different levels, so the probability is 1/256. So very simple. Now if we have this 1/256 probability for one symbol, right, you see 1/256, and then if we just take log 2 1 over what is the probability? 1/256, like this one, right? And so this is for one symbol, and in this way we have for the second symbol, and then in this way we have for the 256th symbol. Now if we just take all of these, that means what? We are basically adding this term 256 times, right? These terms we are adding 256 times. So if I just add up these times, that means this one is gone. We only have this one, right? So this term, and this is exactly, you see, log 2, because it's 1 over, so this is basically 256. Now if you just simplify it, this log 2 256 becoming 8. So the entropy for this image is basically 8. Now see, we had two situations, right? Two images. For the first image, their probability distribution was like that for one symbol we had 1/3 probability, and another symbol we had 2/3 probability, and we found out this entropy is 0.92 for this image. And for another image, This is the probability distribution that for each pixels we had equal probability. This is 1 over 256, and for this case the entropy is 8. Now see, for this image, that means what? For this image, for this information, we need 0.92 bits on an average to represent one symbol. But in this case, we need 8 bits to represent one symbol. So one symbol means 1 pixel level. But we already have this in 8 bits, that when we represent this one in our usual understanding, we usually know that we represent that each levels with 8 bits. So that means what? We cannot compress this image anymore, because entropy mean, when we calculate the entropy, that's the minimum number of bits we must need to represent that information. But this is already the 8 bit, so, and this entropy is also 8, so we can't reduce anymore. So that is, the compression is impossible. But for in this case, how about this one? You see, this one is 0.92. This is our entropy. And but for this one, for a binary image, for a binary image we usually assign 1 bit per pixel. So that means when we assign 1 bit per pixels, but our entropy suggests that it is possible to represent that information by assigning on an average 0.92 bits for each symbol. So that means for this case somehow compression is possible. So why we then measure the entropy? To see that information, whether we can compress that or not. Okay, so that's the idea. So entropy will tell you the minimum number of bits we must need. Okay, the entropy is the minimum number of bits that we must need to represent a information symbol associated with the particular information that we are interested in. So if our information already contain kind of that kind of bits, that means already that's already saturated, we cannot compress. That's the worst case situation. But generally these sorts of distribution, uniform distribution, doesn't happen. Rather the distributions looks like information distribution, the symbol distributions look like this kind of things. When these sorts of things happen, that means we can compress the image because the entropy is less there. Okay, so this is what I explained now. Now with these things in mind, now we understand something like first algorithms or techniques. One technique is called this is one sort of lossless compression technique, and the very simple forms of compression technique is run length coding techniques. Run length coding or run length encoding, sometimes we say run length encoding, so whatever we say. And let's say our example is something like this. Let's say we consider a screen, computer screen, that generally contain the black text. Let's say our text is black on a solid white background. Okay, so that means we had white background and on that we have black text. Now see, if such a situation, if we see one line of that of that screen, just an imaginary line, then what we'll be seeing? We'll be seeing there are many white pixels coming in the blank. You see there will be many long runs of white pixels in the blank space. Okay, so that means when there is think about like this one. Let's say A, B, C, D. Just let's say I'm thinking this one. This is our black background, and let's say this is a white text. Just the opposite of this one. Okay, just think about this when I'm writing. So these are white text on a black background. So if you think about one line, scan line, and if you think about this is 1 pixel, this is 1 pixel, this is 1 pixel, what will happen? In this area the pixels are usually black, and in this area the pixels are usually white. In this area the pixels are usually black. So that means there is long runs of black pixels, but when in text area, long runs of white pixel. Similarly, this is also the case maybe that if we have the black text on a white background, so this area will be long runs of your white pixels, and this will be a long runs of your black pixel, something like that. Now let's say somehow we scan such a line, and let's say this one, that a imaginary line. Okay, so we represent the first pixel is white, the second pixel is white, third pixel is white, fourth pixel is white, and fifth pixel is white, then sixth pixel is black, and in this way this is the pattern. Okay, so now let's say if this is our information for that kind of information or line we are saying, then we can use run length encoding to compress our data. How? So see, first of all, it's a very straightforward technique we can apply. Can you see how many white we have? Consecutive white, that is 1 2 3 4 5. So what we can write is 5 white, and what is next? Next is 1 black, and next is 4 white, next is 3 black, next is 6 white, next is 1 black, and next is 3 white. So, and this is basically your encoded information, or this is compressed information. How? See how many characters we had here. So here we had 21 characters, but here we have only 14 characters. So that means we achieve the compression. So this kind of run length coding is very useful in many cases. Okay, so let's we understand variable length coding. So if you remember that so far we are familiar with fixed length coding. What is fixed length coding? So for example, if you remember that ASCII code, in ASCII code what we had, that any characters on the keyboard that we see A, B, C, or maybe 0, 1, 2, 3, or maybe special character at, or maybe and, or stars, whatever it is. So for each bit we assign, for each character we assign 8 bits, right? You know that. So this is in ASCII table. So this is called fixed length encoding. So that means for each character we used a fixed length that is 8 bit. So that's kind of idea we say fixed length coding. But it turns out that if we use the variable length concept, that means for each character, depending on the application, depending on the message or information, if we assign different number of bits for each characters, so at that times we can achieve some better compression. So such thing is one algorithms, this variable length coding is Shannon-Fano algorithm, and another is Huffman coding. So let's see what is Shannon-Fano algorithm. Now for Shannon-Fano algorithm, let's say we have a message. The message is like this one. Let's say in that we have information or message. So in that information, let's say we have symbol A, B, C, D, E. So that means there are 5 different kind of symbols, and in that message we have this A 15 times, and this B 7 times, this C 6 times, D 6 times, and E also 5 times. So total so okay, so total we have 39 characters or 39 symbol. So if we have total 39 symbol, and see our symbol is A, B, C, D, E. Now how many bits we need to assign generally in our understanding from fixed length encoding? We know that there are 5 different symbols, so that means we have to assign at least 3 bits, right? Because if we assign 2 bits, then we have 0 0 0 1 1 0 1 1. So if we can say this is A, this is B, this is C, this is D, then how about E? So that's why we need at least 3 bits to represent, okay, to represent this symbol. So that means for each character we need 3 bits, and then we have 39 characters, so total we need 17 bits, right? So this is this is the things. But so there are 2 things. What is the total number of bits we need? That is 117 bits, and for each character we need 3 bits. Okay, now how about let's see first that is it possible to compress this information. Okay, so and to check that we need to calculate the entropy. So how do we can calculate the entropy? So definitely we already know. So what is the probability that the occurrence of A, because this is 15 times occurrence out of 39 times, so probability is 15 over 39. And what is the probability of B? It is 7 over 39. This is 6 over 39, and in this way 6 over 39 and 5 over 39. Now if we just calculate like this one, that let's say we multiply this probability 15 over 39 multiplied by log 2, 1 over what is the probability, 15 over 39, right? So this is the first terms we calculate to calculate the entropy. And the second term is 7 over 39 then log 2, 1 over 7 over 39 plus in this way. So if we just do all of these things, and if we just then calculate, then we will see this, you see it's already log 1 over p is calculated. So you just multiply this 15 over 39 with this one, and this 7 over 39 with this one, and then you sum up all of these things, then you will see the entropy will be coming 2.18. So because entropy is 2.18, but as we see that in fixed length encoding we have assigned 3 bits for each symbol, so that means what, there is a possibility that we can compress this information, or in another word, that there must be some coding technique so that we can compress this image. That means we can assign less number of bits to this symbol on an average, and still it is possible to represent that information in computer. So that's the idea, and Shannon-Fano algorithms can do this very well. So let's have it do this. So the very simple thing is, let's say we have total is A, B, C, D, E. So this is our total information, right? So total symbols, I mean exactly the source of symbols, set of symbols. Now see, we'll divide these things into 2 parts, okay? And we'll divide in such a way so that let's say we divide, this is one part and this is the second part, or left hand and right hand. And we'll divide in such a way that almost in each part almost equal number of symbols we have. For example, if we take one part like 15 plus 17 is 22, and in this part we have so this is becomes let's say 22, and this is becomes 17. So that is 6 plus 6 plus 5. So now one may say, no, I will be taking in one part ABC and another part DE. Then what is total number here? Total number will be something like maybe 29, and in this part will be 11. So the difference is huge, right? So this is the optimum division. So this is almost 5, 22 and 17. This is the lowest difference if we divide in this way. So this is the differences, okay? So okay, so now you have A, B here, and then you have C, D, E in right branch, okay? Now again, because it only have 2, definitely you have A and one is another is B. Now how about C, D, E? And because C, D, E, so you just take in one side let's say 6, and another side 6 and 5. So this is become actually 11. So if you take in this side 6 and this side 5, you see this one become 12 is 5, and you see this is the minimum difference compared to this one, right? So that's why the better is you just will be taking C in this side and DE in the right side. And because you already have 2, so just we can divide in this way. Now once you have this sorts of tree, now you assign every left branch you assign 0 and right branch 1, 0, 1, 0, 1, 0, 1, and then you found out the code for each word. So for example, what is the code for A? The code for A is like this, 0, 0, 0, 0. What is the code for B? So 0, 1. So code for B is 0, 1. What is the code for C? The code for C is 1, 0, 1, 0. What is the code for D? The code for D is 1, 1, 0, 1, 1, 0. What is the code for E? So this is 1, 1, 1, 1, 1, 1. So you see, so this is how we can do so. That means for A we assign 2 bits, and for B we assign 2 bits, for C we assign 2 bits, for D we assign 3 bits, for E we assign 3 bits. And if we do so, then how about, you see, if we assign 2 bits for each A, so how many A? We have 15 A. So how many number of bits we need to represent all the A in our information? That is 30 bits. And similarly for B we need 14 bits, because that is 7 multiplied by 2, and then you have 6 multiplied by 2, and then you have 6 multiplied by 3, and then you have 5 multiplied by 3, and we need total 89 bits. So see, before compression we need 1117 bits. After compression we need 89 bits. So compression ratio that we achieve is 1.31. So that means you just divide this one by 89 and then you get 1.31. And that's exactly we applied something like Shannon-Fano algorithms. Okay, and this is why this is variable length coding. You see, now for A we have we have assigned 2 bits, but B also, C also, but for D and E we assign 3 bits. Now why it works? The reason is we already know that A has been used many times, you see, compared to E. So A has been used 15 times compared to E. So if we use fixed length coding for both A and E, it is wastage of bit. Rather we can assign less number of bits, let's say 2 bits to represent A, and whereas we can use more number of bits to represent E. We know that E will be used just few times compared to A, so that's why it doesn't matter that we assign higher number of bits for E, because we will use this E fewer number of times compared to our this A, B and C. So that's the idea why variable length coding works. Now Shannon-Fano algorithm is good, but soon it was outperformed and overtaken by Huffman coding. So Huffman coding is optimal in a sense compared to Shannon-Fano algorithm, and this is how it works. But let's say directly we can go for the algorithm execution, that how it works, then you will understand it. Let's say again we have information, and in that information we have, let's say, these symbols A, B, C, D, E, F. There are 6 different kind of symbols, and the number of symbols in that information is A 45 times, B 13 times, C 12 times, and so let's say write this one. Let's say A have been used 45 times, and B have been used 13 times, C has been used 12 times, and D have been used 16 times, E have been used 9 times, and F has been used 5 times. Okay, now how we can construct this one is very easy. From here, let's say we chose the lowest 2 numbers, and lowest 2 numbers we know this is E and F. Now let's say what we do is we just take this E and let's say this 9 and 5, and let's say the 5 we take in the left side, and let's say 5 we take in the left side and 9 in the right side. So and then what we do, we do this kind of things. Okay, just we draw in this pattern that 5 and 9 plus 14, and this 5 came from E and this 9 came from F. Okay, this is the pattern we need. And we found now using this 5 and 9, we found this 14 is the new number. And what we do is we just insert this 14 in our new list. Okay, now you see, now you again find which 2 are the minimum numbers. Now we can see that minimum numbers is this 13 and 12. So if this is the case, now let's say 13 and 12 means, let's say 12 in the left side and 30 is in the right side, and this is came from C and this is came from B, and if we just add up this together it becomes 25, and just we draw in this pattern, and this is exactly we did here. Okay, so you see this 5 plus 9 is become 14, and this 12 plus 13 become 25. So this is something like that. Now this 25 come into the list. Okay, this 25 now come into the list. Now again we search in the new the minimum 2. The minimum 2 is in this case now is, you see, this 16 and 14. So you see 14 we already have here, this is the 14. So and this 16 is new, and because this 14 is the lower than 16, we keep 14 in the left side and we take 16 is the right side. Now we add up this together and we got 30. Now we just eliminate out this 16 and 14. This 30 is the new number in the list. And now you see again we find out the minimum 2, and now in this times our minimum 2 is this 25 and this 30, right? So and we already have this number here, so now this add this 25 and 30, now it become 55. Now you just eliminate these 2 numbers and bring this new 55 in the list. Now we have only remaining these two numbers, 45 and 55. So because 55 is larger number, so keep 45 in the left, and just see 45 and 55 you just add up, then you become 100, right? So now in this way we now have finished all the numbers, and then we come up with this kind of tree diagram, right? A tree diagram. And definitely when you construct this tree, be careful that every time when you add up, and if this coming from this, you just write which one is coming from. For example, this 5, this 9, this 12, this 13, and this 45, it originally came from here, right? So that's why we write this D, this F, this E, this B, C, and A. Okay, once you have that, now what you do, you assign all the left branches 0 and all the right branches 1. So this is 0 and this one is 1. Similarly, this is 0 and this is 1. Similarly, this is 0, this is 1. Same way, this is 0, this is 1. And definitely this is 0, this is 1. Now once you assign 1, 0, so now you go back and you just see what is the code for A. The code for A is just 0, and this is exactly the code for A. And what is the code for B? Now code for B is, because the B is here, this is 101, and exactly you see code for B is 101. What is the code for C? 100. You see 100. What is the code for D? The code for D is something like 111. Yeah, 111. What is the code for E? 1101. So 1101. And then code for F is 1100. So this is what it is. Again, you see this is the fixed, variable length encoding. Only one bit we need for A, 3 bits for B, C, D, and 4 bits for E and F. And you can find out this compression ratio. You can calculate the compression ratio, right? Because before and after in the same way that we did before. So this is the Huffman coding. Now see, both Shannon-Fano algorithms and Huffman coding, if we need to work on that, we need to have this information, right? That which symbols, how many times occurs in one information. If, for example, we have a particular image, or let's say we have a message, we know that which brightness level, how many times are there, or which character, how many times are there. But in many cases, we don't have that information, right? For example, in multimedia applications where this, information is live streaming, and so we don't know that what are the number of some particular characters, what are the number of particular pixel levels we have. So in that situation, we cannot apply directly this Huffman coding. Rather, we need to modify this Huffman coding or Shannon-Fano algorithms. That's called modified, or more appropriately called adaptive Huffman coding. Okay, in adaptive Huffman codings means this kind of statistics, this kind of table, or we can say probability or statistics, we generate as the information comes in, we generate. So adaptive, dynamically. Okay, so such dynamically one algorithms is LZW algorithms. So it's more appropriately called Limpel-Ziv-Wells algorithms. So it is also known as dictionary based algorithms. Now this dictionary based algorithms is not variable length coding. It's also variable length coding, but it's use fixed length code words, okay, to represent variable length strings of symbols. What is that? So that means think about a word like pen, and let's think about another word pencil, right? Okay, so this is basically a new word, and this is another word. What we do for this word, we use, let's say, fixed number of bits. Maybe let's say 5 bits or 10 bits or 9 bits, whatever. Let's say 5 bits or 10 bits we represent, or let's say 8 bits we represent for this word. Same for this word, we also use 8 bits. So that means we use fixed length encoding, but this word itself is variable in appearance, right? Or in shape. So that's why it is still a variable length encoding, but we use fixed length code words. So what is code word that I'm saying? It is very simple terminology, not difficult. You see here, so this single one code for this A is called code word. This is also a code word. This is also a code word for C, code word for D, and this all together, all the code words together, you say one code. Okay, Anyway, so this LGW we use something like where we use this one, this GIF image, WinZip, and many other applications we use this LZW encoding, and we don't need to there's things how it works. Just that what is the concept of variable length, what is the concept of fixed length coding, how Shannon-Fano, basic Shannon-Fano algorithms, Huffman coding works, and what is entropy, what is the importance of entropy, and what we mean by compression ratio, how compression ratio works. So these are some basic terminology that we used. And by the way, this run length, this run length encoding, or we say run length coding, these Shannon-Fano algorithms or Huffman coding, all of these algorithms are basically lossless compression. We don't lose any information. So this is what I had for you for lossless compression techniques. Now we will move to lossy compression techniques in the next part. And this is one example that you can do yourself, you can practice. So for example, let's say this is one information or message. So this is a good book, and space is also a symbol. You can calculate the entropy, you can apply Shannon-Fano algorithm, and you can also apply Huffman coding, and you can see which one provides better compression. This is for yourself. Okay, so now next move to the next part. This is lossy compression.